Hello, my name is Rafael Herrera here in CIMAT. It is a pleasure for me to introduce Fernando Galaz Garci, a professor of the University of Durham, who's going to present his talk about metric geometry of spaces of persistent diagrams. But just before he starts, let me tell you that it's a great pleasure to introduce him, because he's a friend of CIMAT for many years, since his very early youthful years. He was a student here in the BA program, the University of Guanajuato and CIMAT share. So, and he has been a great friend to CIMAT over the years, and well, we are very proud of him, and well, we thank him very much for his talk, which I'm sure is going to be very, very interesting. Thank you, Fernando.
Thank you very much, Rafael. Thank you for your very kind words. So it's a pleasure to be here, and thank you everyone for coming. So I thank you to the organizers for the opportunity to give a talk in this seminar. So so I will talk about metric geometry of spaces of persistence diagrams, and so this is so the talk is divided into two parts. So one is about metric geometry. So I work in geometry. So I will talk about a connection between metric geometry and objects that arise in topological data analysis, which are persistence diagrams, and actually the sort of the spaces of persistence diagrams. So if you have questions, please feel free to ask them. So I will, of course, be happy to answer them if I can. So right. So what is the general theme of the talk? So it's the idea is to try, if you're given some space, right? Maybe it doesn't come equipped with a notion of geometry. Maybe it's just a topological space, or maybe it's the metric space. So one can ask this very general question whether the space supports some nice geometry. So of course, nice is just up to personal taste. But here we're going to talk about curvature, and so this is the question the talk is going to be focused on. So the idea here, the spaces arise from topological data analysis, and the connection is with metric geometry. And in particular, we're going to talk about spaces of persistence diagrams, and the sort of the type of geometry that we want to put on these spaces is Alexandrov geometry, or the structure of an Alexandrov space. So since the seminar is more about applied topology, I will focus first on the part that might be less familiar, which is the part about Alexandrov spaces. And so the goal is to see that some certain class of spaces of persistence diagrams actually admit the structure of an Alexandrov space. And so what is an Alexandrov space? That's the first half of the talk. So the first part, or the departure point, is so Alexandrov spaces arise in differential geometry, in particular in Riemannian geometry. So it's okay, you don't need to know what a Riemannian manifold is. So through the first part of the talk, so you can just think of the sphere, say. So this is a Riemannian manifold. So just think of the sphere. It has a tangent plane here. This is in R3, and here R3 has an inner product. So you can take this induces an inner product on the tangent space, and that lets us measure lengths of tangent vectors to curves and also angles. And in particular, it induces a distance on the space, on this sphere. And well, one of the fundamental invariants is curvature. So once you fix a Riemannian metric, meaning like a way of assigning lengths and angles to tangent vectors via an inner product, this one has curvature, and what curvature is, you can think of it as a number that you assign to a two-dimensional subspace of a tangent space. This is k of pi. So this is a real number, and but the goal here in this first part is to make sense of these four spaces that are not necessarily smooth. So it's only spaces that have that are metric spaces. So one has to sort of identify some properties of curvature that are not really, that do not arise via the smooth structure, but rather one can express by distances. So if you, so one way of detecting curvature, for example, on the surface, is by means of triangles. So for example, here on this saddle surface, this is a triangle that looks sort of thinner than a Euclidean triangle, and that the sides are geodesic curves. So these are curves that are minimize the distance between these points, and this sort of idea that sort of a triangle that is sort of thinner than Euclidean is related to having negative curvature. Then a regular Euclidean triangle is like zero curvature, like flat plane, and then a triangle that looks fatter or thicker than a Euclidean triangle, that's related to having curvature greater than zero. So now, so we want to make sense of this for metric spaces, and we're going to look at a particular class of metric spaces called length spaces. So these are path-connected metric spaces where the distance is given by the infimum of the length of curves. These are certain classes of curves for which we can measure the length. So how do we measure the length of a curve? So we can take points in the curve, like, and then, well, this is a metric space, so one can, so this is, imagine this is a curve on the plane. So the distance between these consecutive points is given by the length of these straight lines, right? And one can then take finer and finer partitions and take the supremum, if that is finite, right? One says the curve is rectifiable, and one takes the infimum. And actually this definition, this is exactly how the distance on a Riemannian manifold is defined. So one looks at metric spaces where the distance sort of looks like the distance on a Riemannian manifold. And as in, right, like in Riemannian manifolds or on the plane, right, the shortest curve between two points is a straight line. But one also defines curves, geodesic curves. So those are curves that minimize the distance between their endpoints. So the length is the distance between the endpoints, and then, well, and then a particular class of length spaces are geodesic spaces. So a length space is a geodesic space if any 2 points can be joined by a geodesic, by a shortest curve. And then, if you're familiar with Riemannian geometry, then, for example, for complete Riemannian manifolds, those are geodesic spaces. So this is good because, for example, this lets us talk about triangles whose sides are geodesics. So, as in this picture here, right? We may take 3 points and then join them by geodesics. So we want to look at spaces that have that property, and then we want to look at triangles in spaces that we understand well. So these are called model spaces. they denote them by S2 sub k. So this is a space with constant curvature k. So this is the complete simply connected two-dimensional Riemannian manifold with curvature k. Okay, so these are, one knows that there are only these three possibilities. There's the round two-dimensional sphere if k is positive. And here's a picture, right, of the two-sphere, the round two-sphere, the Euclidean plane. So here's a piece of the Euclidean plane, and the hyperbolic plane if curvature is negative. So this is one of the models for the hyperbolic space. And here, for example, one can see these triangles. So this is a Euclidean triangle, right? These are the angles add up to pi. Then in hyperbolic space, the triangles are sort of thinner, so the angles, the sum of angles is less than pi. And here on the sphere, if one takes a triangle whose sides are geodesics, the sum of angles is greater than pi. So we want to compare now triangles in a given geodesic space with triangles in these model spaces, and we want to make sense of a notion of having curvature greater than or equal k. So for that we have to define triangles. So a triangle in a geodesic space is consists of three different points, p, q, r, and three geodesics joining the points, one from p to q, p to r, and q to r. And so this triangle exists in the space X, and now we want to compare it with a triangle in the model space. So for that, one defines a comparison triangle. So this is a triangle that has, again, triangle PQR bar, whose sides have the same length as the sides of the triangle in the metric space. So depending on K, right, a comparison triangle may exist or no, may or not exist. So for example, if K is positive and very big, that means that you're in a very small sphere, so the triangles cannot be arbitrarily big. Okay, so now we need to define some property with which we can compare distances or triangles in the metrics in the geodesic space X with triangles in the model spaces, and this is this property Tk for 3 points in X. So this is a triangle, a geodesic triangle in the geodesic space X. So we have 3 points, P, Q, R, and then the sides are geodesics, so shortest curves. And then we look at a comparison triangle in the model space with curvature K. So this is a triangle with vertices P bar, Q bar, and R bar. So this is a comparison triangle, so the lengths of the sides of the corresponding sides are the same. So this side has the same length as this one. This side has the same length as this side, and this curve from Q to R has the same length as this one. So here you can imagine maybe this is like a triangle and a sphere, and this is a Euclidean triangle. So okay, so we have these two triangles, and now we look at this curve, and we take a point here, S. Now this curve has the same length as this side, so there is a corresponding point, S bar, that is at the same distance from Q bar as S is from Q. Yeah. And now what we do is we look at the distance, or at the shortest curve from P to S here, and then we compare it with the distance or length of this shortest curve from P bar to S bar. And then we say that this property holds if the length of this curve, of the distance from P to S, is greater than or equal the distance from P bar to S bar. So one way of, or maybe imagining it is that maybe you're here and you want to walk to here, and then you need to walk at least as long, as much as walking from here to here. Okay? So this is this property TK. So let me just write it again or go over it again. So what we have is this is a geodesic triangle, PQR, and then we have a comparison triangle. And what we want is that for any point here, right, from Q to R, the distance from P to S is greater than or equal the distance in the comparison points. So where is this coming from? So, well, maybe a few comments before. So this is expressed purely in terms of distances. So here we know how to measure everything. Here we only know how to measure distances. So this is a nice Riemannian manifold. Here this is only a metric space. And well, where is this coming from? So this is actually when X is a Riemannian manifold with curvature greater than or equal K. This is actually, this holds. This is a theorem. This is called Toponogov's theorem. So this is Toponogov's theorem for manifolds, for Riemannian manifolds, expresses the curvature in terms of metric invariance of distances. And then one can take that as a property and turn it into a definition for having curvature greater than or equal K. So then, so that's what an Alexandrov space with curvature bounded below by K is. It's a complete geodesic space where property TK holds locally. So for every point, one can find a neighborhood where this triangle comparison holds. And this is, so in particular, Riemannian manifolds with sectional curvature greater than or equal K are Alexandrov spaces. So this is like a metric generalization of Riemannian manifolds with curvature bounded below by K. So these are not necessarily smooth, right? So for example, this is an Alexandrov space with curvature greater than or equal 0. So it's so here it's flat, these spaces, and somehow, but if you one can think maybe all the curvature is concentrated on these vertices, and but it's topologically a sphere. This is not an Alexandrov space. It doesn't have curvature bounded below. So you may think if you take triangles here, geodesic triangles, they look like for example, a neighborhood of this point. So every triangle looks like a T. So if you want to find a comparison triangle, you need to take thinner and thinner triangles and hyperbolic space, but there's no, you don't have a lower bound. So in general, you may, so throughout this part, you may think of this space or Riemannian manifold, or actually the round sphere is fine. And so what are important properties of Alexandrov spaces? Well, geodesics do not branch, so you don't have this phenomenon that these are shortest curves and then suddenly you have a branching point. Then this triangle comparison property holds globally, not only for triangles around a sufficiently small neighborhood of a point, but for any geodesic triangles. And so they have they cannot be sort of too bad in the sense that the Hausdorff dimension is an integer or infinity. If you don't know what the Hausdorff dimension is, doesn't matter. You can think of sort of again of a Riemannian manifold of dimension n, or an infinite dimensional space, for example, a Hilbert space. So, for example, fractals are not Alexandrov spaces with curvature bounded below. So maybe just as a remark, one can also reverse the sign here of this inequality, and that one would get curvature bounded above by k. But that's but here we're going to talk about spaces with curvature bounded below. Okay, so maybe are there any questions so far?
Do they have a special name for spaces with the curvature bounded above?
Yeah, it's like cat K.
Okay, thank you.
Right. So maybe you've heard of those. So, for example, this space is like cat 0. Okay, so examples, right? Like Riemannian manifolds with curvature bounded below by k. One can also take convex subsets of Rn. Those have non-negative curvature. One can also take topological constructions, for example, suspensions or cones. So this is for example, the suspension of a circle, which is topologically a two-sphere. But in general, you can take a space with curvature greater than or equal 1, and one can take the topological cone, and one can put a metric on it so that you have non-negative curvature, or the suspension of such a space has positive curvature greater than or equal 1. One can also glue spaces with finite dimension. So, for example, here this is a 2-disk in Euclidean space, so this is a convex subset of R2, so it's an Alexandrov space. Here you have another copy. One can define what the boundary is, so in this case this is the topological boundary, and one can glue them, and that is again an Alexandrov space. So here this is topologically S2, right? But it's flat except for these curves. One can also take quotients by groups acting by isometries. They're compact or have closed orbits. That's sufficient. And this is also actually how they arise in Riemannian geometry, or actually they as limit spaces of Riemannian manifolds. So you can think of, if you look at the space of compact metric spaces, there is a metric, a distance on that space called the Gromov-Hausdorff metric. So then one can think of compact metric spaces as points. So it makes sense to talk about sequences and convergence and so on. So and then in the case where you have a sequence of compact Riemannian manifolds of the same dimension that have the same lower curvature bound, if the sequence converges in this Gromov-Hausdorff sense, then the limit is an Alexandrov space with the same lower curvature bound. And so this has been very useful in Riemannian geometry. If you want to understand a certain class of spaces, say that is pre-compact with respect to the Gromov-Hausdorff metric, when you look at its closure, you're forced to look at Alexandrov spaces. All of these are here finite dimensional, and also it has Hilbert spaces. Those are infinite dimensional with non-negative curvature. Okay, so just let's continue. So remember, the goal is to say, well, some spaces of persistence diagrams, what the connection with this is. So one can understand the local structure, so one can define angles, and then one has tangential directions, and there is something called the space of directions, which in the Riemannian case, or in the case of the sphere, it's just the unit tangent circle, or for Riemannian manifold is the unit tangent sphere. So, and this is in the finite dimensional case, this determines the local structure in the following way. So one can show that if the space is finite dimensional, then this space of directions is an Alexandrov space of curvature greater than or equal to 1. And the dimension is 1 less than the dimension of the space. And so this, in a way, this shows or suggests that spaces with positive curvature are special, right? And this theorem of Perelman says that the local structure is controlled by the space of directions. So if the dimension is finite, every point in the space has a neighborhood that is pointed homomorphic to the cone over the space of directions. So going back to the manifold case, right? In the manifold case, the Riemannian manifold case, the space of directions is a sphere, and then so if the sphere, it's actually a round sphere of radius 1, so it has actually sectional curvature equal to 1, and it's it's 1 dimension less than that of the manifold. And then one learns in the if you've taken a Riemannian geometry course, there's one proves that every point has a neighborhood that's diffeomorphic to a neighborhood of the tangent space via the exponential map, and this is a neighborhood of the origin in the tangent space via the exponential map, and that is a ball, and a ball is a cone over a sphere, and that's so this is the generalization of this fact from Riemannian geometry. But here one doesn't have a smooth structure, only metric spaces, and this triangle comparison, so one has to do a lot of work to obtain the similar result. So now, what does one know about the topology? Well, not much. So in dimension 1 and 2, so Perelman proved that an Alexandrov space is always a manifold, possibly with boundary. So they are either, so for example, in dimension 2, there are surfaces, right? And then this in particular means via this theorem of Perelman, one knows what the local structure is, because we know the spaces of directions in dimensions 2 and 3. So for example, if you know that in dimension 1 space is a manifold, so it has to, if you don't have boundary, it has to be a circle, and the theorem of Perelman implies that the space has to be locally looks like a disk, so it's a two manifold. Then in dimension 3, this I proved with Luis Guijarro. So one can characterize the spaces as either topological manifolds or quotients of 3 manifolds by certain involutions. But and then via this one knows the local structure in dimension 4. But then in higher dimensions, it's not known. Other things can happen, so they're not as well behaved. And then if you remember, it's possible to have infinite dimensions. So actually, in infinite dimension, it's even worse, or there's very little known. So it's in particular many of these results I mentioned about, for example, they're not known to hold for in infinite dimensions, and one has to be careful because some of the definitions or some phenomena that happen in finite dimensions no longer, it's not clear whether they hold or what the necessary hypotheses have to be to have good properties in infinite dimensions. So this is actually a big unexplored part, and it relates to the second part of the talk. Here, maybe there are only few people who have done work on this, Mitsuishi, Cloud, and Yokota, and so this is basically a quick look at what an Alexandrov space is, and in particular, I want to emphasize this last part because this is relates to now we're merging with the topological data analysis part. So, okay, so now on to topological data analysis. So I'm going to again just quickly remind you or talk about what the main idea is, just very succinctly. So so what one does, or these persistence diagrams, where do they arise? So what is the idea with persistence theory, right? So one has, so imagine this is just R2, right? One has a point cloud, or just infinitely many points, and then just a very high level discussion is that one can construct some complex out of this data, and one gets some filter simplicial complex. So this is sort of parameterized by, say, for example, the non-negative real numbers. And then out of these, one can compute something called the persistent homology, and one gets something called a persistence diagram. So we're going to actually just define persistence diagrams in a, so this is just as a motivation of where the objects are coming from. And this sort of measures how many sort of generators of these persistent modules. Okay, so so again, this is just the same with words. So we have a data set here, then one has a filtration of simplicial complexes here, and then one gets something called a persistent module, and then one gets here something called a persistence diagram that is so related to these homology groups. And so now, so this is sort of used in topological data analysis, and well, so imagine you have many sort of different point clouds, and then, well, you get different persistence diagrams, and then you want to somehow make sense of compare different persistence diagrams, right? So you want to say, well, are they close? Are they far? Do I have the shortest curves? Can I make this set of persistence diagrams into a metric space? So well, this is something people looked at actually some 2011. So more just in a generalization of this, or this includes persistence diagrams appearing in the way that I talked about in the previous slide. So just for the rest of the talk, or well, let's just formalize this. So then a persistence diagram is going to be a multi-set, so whose elements are a countable collection of points in R2, and you don't want these points to be the same, meaning you don't want them to be in the diagonal. And then you add to this multi-set countably many or infinitely many copies of the diagonal. So, okay, so what is special about the diagonal? So, going back here, I mean, this is related to the birth and death of generators in the homology. So things that are in the sort of in the diagonal is sort of like they are born and die instantaneously. So one doesn't want to consider those, but this is put there. I will hopefully it will be clear why one has to consider these copies, right? So you may have a different number of points in your persistence diagram, and then if you want, like, so basically the thing is, the persistence diagram has countably many points, right? Some are points in R2, some are copies of the diagonal. But so you can actually, you have a bijection between the elements of a persistence diagram, but you want to compare then. Having infinitely many copies of the diagonal lets you compare diagrams that have a different number of points in R2. So I will show that with a picture. So, but now, as I mentioned, we want to talk about distances. So we want to make this into a metric space, and there is a family of metrics called the Wasserstein distance that are parameterized by a number p that goes from 1 to infinity, and it's defined in the following way. So you take two persistence diagrams, and then you look at the infimum of the distances, the sum of the distances to the p between x and phi of x. And here this phi is a matching between the diagrams. So this is just a bijection. And this is if p is 1 or is finite, from 1 to strictly less than infinity. And then if p is infinity, then one looks at the supremum of the distances. For this, we fix a bijection, and then you take the infimum. So this is called the bottleneck distance in this data analysis literature. So this is actually so these are Wasserstein distances, and so these are these matchings between two diagrams. So these are bijections. So here, for example, we match them with this diagonal. So these things are, you can consider them as copies of the diagonal. Okay, so now this space comes with a distinguished point. So there's the point that has no, that consists of only copies of the diagonal. It doesn't have points from R2. And this is, you can think of it in a way like the origin. And then one can define this space, so D sub P of R2, the diagonal, as the set of diagrams that are at finite distance from call it the empty diagram, and it's endowed with the p-Wasserstein distance. So this is a space, and then it is actually a metric space. And then in this same paper, Mileko, McCurdy, and Harrer, they showed that this space is complete. It's a complete and separable metric space for any p from 0 to 3. And well, okay, and where does the connection with Alexandrov geometry come from? So this is a theorem from follow-up paper by Turner, Mileko, McCurdy, and Harrer, and they proved that if P is 2, this is actually an Alexandrov space with non-negative curvature. Which, so this is very intriguing. So, I mean, there's this unexpected connection, and then, well, if you're a geometer, well, you immediately want to know, okay, so what does this space look like? What is the geometry of space? And also, in particular, these spaces this is an infinite dimensional space, and so it's an unexpected example. So so this caught our attention, and we decided, well, we looked at this, and so, well, but let's see, so what do we have so far? So we have a Rn, right? Actually, we had R2 and the diagonal, but one can do the same thing for Rn. And from here, it should be 2. But, well, we get this space, the space of persistence diagrams, with the p-Wasserstein metric. And as we saw before, this space has a distinguished point. So what we're getting is from this pair, so we have our 2 here with this special subset, the diagonal, we are getting a pointed metric space. So here, this is something called the metric pair. And for each P, we are getting a pointed metric space. So we're getting a family of metric spaces. So if one goes through these papers, one can see that like most of the arguments are purely metric and actually do not really rely immediately, or it's possible to push them so that they don't rely on this space being R2. So one can actually just consider metric spaces. So one can take X just to be a metric space, a closed subset, and then, well, ideally, one would like to get something like this, to get a pointed metric space that in such a way that when you do this construction, or when you plug in R2 and the diagonal, you get this space of Euclidean persistence diagrams. So we want to find a way to assign to a metric space, a pointed metric space, that's like a generalized space of persistence diagrams. And so, right, so this is the context, or the setup is to look at metric pairs. So these are just the pair X and A, where X is it's a metric space, and A is a non-empty closed subset. And now we want to define what is a persistence diagram in this metric pair. These are countable multisets in points with of points in X with countably many copies of A. So this is just basically we're just exchanging R2 and the diagonal for X and A. So, and now one can also define the Wasserstein distance for diagrams in these metric pairs. So this is exactly the same definition as before. The only difference is that here is in the previous definition, we had the distance in R2, the Euclidean distance, but this is just the distance, so you can just change that for the distance in your metric space. And now you again define this to be the set of diagrams in the metric pair. that have finite distance from this special diagram. Like now, instead of the diagonal, we have this distinguished subset endowed with the p-Wasserstein distance. Okay, so this is now a general framework, and one can ask, well, how much can one push what was known? So were the previous results really a consequence of having R2, or is this something actually more general? So here the theorem is coming, and then once you have this setup, actually, this is one realizes that you actually have a functor from the category of metric pairs with relative Lifshitz maps. So these are maps that send the metric pairs to metric pairs, and it sends it takes values in the category of pointed metric spaces with pointed Lifshitz maps. Okay, so this is basically the realization of this here. So you have a metric pair, you get a pointed metric space, and here, this is what we have. This is from a metric pair, we get a pointed metric space, but we think of this as a functor, right? For each p, we get a pointed metric space via this construction. And so here we get this is the distinguished point, and here we get it sends a function, these relative Lifshitz maps, it sends them to these pointed Lifshitz maps. And this, well, and for example, if you have a group action here, it passes to a group action on this generalized space. So this behaves well with respect to these maps. And right, so then you can ask, before we had a family of, for R2 and the diagonal, we had this family of pointed metric spaces. Now for each metric pair, we have a one parameter family of metric spaces. And so once you look at this from this functorial approach, you can ask, well, which properties of this space, of this metric pair, are preserved by the functor, right? So that's another way of framing these results that say that if for example R2 is complete, and then the space of diagrams was complete. So now you can ask, well, is completeness preserved? Is separability preserved? What about lower curvature bounds? So this is the theorem. Well, some of the results we obtained with Mauricio Che, who is a PhD, my PhD student here at Durham, Luis Guijarro, who is my collaborator with his other work on Alexandrov spaces, and Ingrid Membrillo Solis, who is in Southampton and London. So this is okay. So so how much of this holds in this general setup? So here we have a metric pair, and we fix p1 to infinity. So then, actually, well, many nice things are preserved, right? So if this is complete, then the space of persistence diagrams is complete. If this is if X is separable, then the generalized space of persistence diagrams is also separable. Now here, one has to ask, R2 is proper. So this was something that we identified as a property that if you assume this, then one can show that there exist optimal bijections between diagrams. So this is a technical condition that was known for diagrams on R2, but that is necessary. That is then useful to prove that if the space is proper and geodesic, then this is geodesic. So now if we are sort of going towards asking about Alexandrov spaces, so these are the properties that you need, right? Complete and geodesic, and then so this is the analog or the generalization of this result about the space of diagrams in R2 being a non-negatively curved Alexandrov space. So this would be 6. So this one needs it to prove this. So this 0.5 means that sort of the geodesics in the space of diagrams when p equals 2 are sort of what one would expect. They're actually given by curves in the between points in X. So putting all of this together, then one can prove this that if X is a proper Alexandrov space with non-negative curvature, for example, R2, or a Riemannian manifold, compact Riemannian manifold with non-negative curvature, or any other space that you know with non-negative curvature, then its space of persistence diagrams is also a space with non-negative curvature. So then one can also show that these have infinite dimension. So this sort of generates a lot of spaces of non-negative curvature of infinite dimension, and actually we don't know much about these spaces. And so something that we also proved in this paper is that the space of directions at the distinguished point at the empty diagram has diameter less than or equal pi over 2. So this means that this point is really a singular point. But in general, it's not. I mean, the fact that it's infinite dimensional means that one cannot use all the finite dimensional theory, which is what most things are. Well, that's where we have a better understanding of things. So this is some this links back to this question that what can one say about infinite dimensional spaces? And conversely, anything one can say, well, what has this could have applications in these spaces of persistence diagrams, in particular this Euclidean space or the classical space of persistence diagrams is one of these. Now here you may notice that this has infinity is not here. So when p equals infinity, one has to be careful because the space may not be a metric space. It's a pseudo-metric space, meaning you may have two different points, but that are at distance 0. So, but there may not be the same. So still, one can say things about those, and in particular, so maybe another natural question that arises here is that if you think of this as right in this functorial way, you assign to each metric pair, you assign to each metric pair a pointed metric space, and then you can say, okay, I know the Gromov-Hausdorff distance, right? So if I think of these metric pairs as points, it makes sense to. Can I ask about continuity? Are these functors continuous with respect to some metric? And so one can define a notion of Gromov-Hausdorff distance between metric pairs, and then we also prove that this functor, the one corresponding to the bottleneck distance, but this is really a pseudo distance, is actually sequentially continuous with respect to the Gromov-Hausdorff convergence of metric pairs. So meaning that if two metric pairs are close in this distance, then the images are also closed in there's something called the pointed Gromov Hausdorff distance. So further results for the bottleneck distance that there one has to work with different way are that, for example, as I said, this is a pseudometric space, so one can characterize when it's a metric space if and only if you remove this distinguished set, you get a discrete space with the restricted distance. Now one can, combining the previous result, one can actually now also prove that for p equals infinity, if x is complete, then this is also complete. So now putting it together, one knows that this is complete for all p between 1 and infinity. And if this is proper and geodesic, then this is also geodesic. So, and there are also more results. I mean, there are more results in our papers and also from other people. So let me talk. So this generalization had already been sort of considered as from a more algebraic point of view by Bubenic and Elchison, and but the metric properties hadn't been looked at. So then here another thing that is useful is computing Frechet means. So these are also known as barycenters. So if you have, so for example, you want to look at many diagrams and then compute like a center of mass. So this was done by Milejko, Mercury and Guijarro in this paper I mentioned earlier for the space with R2 on the diagonal. Then we also proved this holds in more generality. So then shortly after our work, also Bubenic and Hartzog have results about metric geometry of spaces of persistence diagrams. So that are related. And also there is some interest about embedding these spaces into Hilbert space. And there also, so also Bubenic and Wagner, here they have some results, Mitra and Birk, and more recently Bate and Ana Lucia Garcia Pulido also. So these are different strands of things that one can study, but in general, I think it's like both from maybe if you're doing more persistence or topological data analysis, but also if one is interested in geometry, it's like an interesting sort of interaction between the two things, and even also from more these spaces are infinite dimensional, so also many of the standard rules just do not apply. So there's also some many sort of things to be explored, and so with this, I want to thank you again for coming and for your time, and thank you again for the invitations.
Very fine. Thank you very much for your wonderful talk. I think it's very interesting to see these intriguing results relating topological data analysis and Alexandrov spaces. So by now, are there any questions about Fernando's talk?
Well, I have a question.
Go ahead.
Yeah. Okay. About your first theorem of the three you showed, the first one which has 6 parts. Yeah, in part number 6, is there anything known if X is a manifold, like maybe a 1 manifold or 2 manifold or 3 manifold? What can you say about the dimension or the properties of your space of diagrams, D2 of XA?
Right. Thanks. Yes. I think these spaces will be infinite dimensional, regardless of the dimension of the
okay.
of X. It just immediately goes to infinite dimensional. But that's a good question in the sense that if you take maybe a simple space like a circle or something like that, maybe one can say more things. That's we don't know. Yeah, we haven't thought about that yet.
Okay.
Thanks.
Fine. Are there any other questions?
Yes, I have a question. So, is the D2 space under this functor ever proper for some conditions on X?
No, I don't think so. Yes, but I would have to get back to you on this. But no, I don't think it's not locally compact at the. So yeah.
Okay.
Mm-hmm. Right.
Very fine. Are there any other questions? Hi, Fernando. I know that this is not related to your main results, but I know that you are an expert in Alexandrov spaces. And then I would like you to ask, what can you tell us something more about these Alexandrov three-dimensional spaces?
Right. Thanks. So yeah. So okay. This is here. Right. Yeah. Okay. So these are right. So these are either topological manifolds or I wrote here these quotients. So basically, these are quotients of an this is an orientable three manifold with an involution that reverses orientation and that has isolated fixed points. So what this means is that these spaces locally look either like a manifold or a cone over RP2. So what this means is that, so one can see that also from here, right? So in dimension, the space of directions of a three-dimensional space is a two-dimensional Alexandrov space with positive curvature. And if you don't have boundary, those are only S2 and RP2. So here, right here, there's also a lot of work to do. So thank you for the question. So here, the underlying topological space is either a manifold, so meaning if you want to study the topology or geometry, this is you're in the manifold case. But then you have this other sort of one half are manifolds, and the other half are these spaces that look almost like manifolds, except for a discrete set of points. Well, actually, if the space is compact, finally many points, that look like cones over RP2. So that means that if you take away these cones, these spaces are put together out of a 3 manifold that's non-orientable, that has boundary components P2, and then you close them with cones over RP2. And here again, also almost nothing is known for these ones. But their structure is sufficiently simple that one can hope to obtain sort of nice results. So this is also, yeah, this is another talk. Yeah, but thank you. Yes, this is actually, if you're working 3 manifold topology, I think this is an interesting set of spaces to study, especially I'm very interested in understanding that. So if you have ideas, I'd be happy to talk. Thank you.
Fine. Any other question?
Hi, thanks. Yeah, thank you for your talk. It's very interesting to see these connections between Alexandrov geometry and TDA and persistence. So I guess I'll go for a technical question first, just because I'm very curious about this. Do you think that the item 6 in your main theorem could also be shown in the case of RCD spaces, so that you would substitute the Alexandrov condition by this other metric condition? I know this is just for like experts on this topic, but I was curious about this.
Right, yes, that is actually something that we have been thinking about.
Well, yeah, I mean, I guess with Luis and with Mauricio,
Well,
that's
yes,
probably what you're working on.
that's a natural question. So maybe for the non-experts, so there are other types of curvature in Riemannian geometry, like sectional curvature is related to triangles, and then there's another weaker notion called Ricci curvature that's related to volume. And then in the same way that Alexandrov spaces generalize sectional curvature bounds, lower bounds to metric spaces, these RCD spaces generalize lower Ricci curvature bounds. And now so that's a very good question. It's very natural. The challenge here is that these spaces are not finite dimensional. So as I mentioned, Ricci curvature is related to volume, but volume is a measure. But the challenge, so these RCD spaces, you need a measure, right? So I think the first obstacle is that, well, how would you define a measure? It's the measure.
Yeah, that would be the RCDK infinity type.
Right. But you need right. But first here you need to define a measure, and that's not.
Yeah, it's not clear.
Right. That's the first obstacle. Yes. Yeah, it would be. Yeah, right. I mean, again, going back to this theme that finite dimensional, right? So in the finite dimensions, it's known that non-negative Alexandrov curvature implies non-negative Ricci curvature in the RCD case. I think that's Petronian's work, but that's for finite dimensional spaces. So one would like an infinite dimensional, yeah. So, but yeah,
Great, thanks for the answer. It's nice to know that you're working on that. And maybe just another curious question: do you have some example where you could substitute the usual R2 of the space of diagrams for something like, say, T2, S2, like somewhere where it would come up, like on a specific persistence diagram setup, just to have something in mind?
Right. Yeah, that's also a good question. Yeah, I think, I'm not an expert in topological data analysis or persistence, but I mean, I think, I know there's these things called multi-parametric persistence, right? And so you can think of X, like for example, in the case of R2, this Right. Like here, this parameter, right? This is a parameter for your complexes. And this R2 is like, well, it's the R. That's it. It's related to having this parameter being R. So if you had, like, you can think of this X, you could think of it as your, like if you had a space of parameters, then you could take the cross product, right? And that would be like your metric space. So this is, this could, one could frame, I think, this multi-parametric persistence in this. I think one of the challenges is that I think if the notion of persistence diagrams for this multi-parametric persistence is not, I think it's maybe not fully worked out, but I'm not 100% sure. But yeah, I mean, you can put, for example, if you're parameterized by like a circle, right? If your parameter is a circle, then you have a circle cross a circle is T2, right? And then you have a curve that's the diagonal, and then that's the example that, for example,
I was trying to think if there was something like that, like some sort of periodic version where the parametrizing by a circle would make sense, and that would kind of apply there. But yeah, thank you for the example with the multi-parametric one. I think that's a very good one, and that it changes, I guess, R2 by R2, and then maybe getting a compact one would be interesting.
Right. So yes. So I think people are looking, or there's work on that, but in a particular actual like application, I don't know. But yeah, but if you had like a cyclic parameter, like a circle, then that would enter into this. So.
Great. Thank you very much. Thanks.
Thank you for your questions. Thanks.
Very fine, Fernando. So I think maybe it's time to finish this wonderful session. And then we have to say again, thanks to Fernando for this superb talk. Thank you, Fernando.
Thank you very much, everyone. Thank you for the invitation. Thank you.